Good morning and welcome to our fourth lecture on statistical mechanics. In the last lecture we have demonstrated the effectiveness of this method whereby even without calculating the exact value of omega, just by considering the properties of omega, which is the number of microstates for a system in a particular macrostate, just by considering the properties and its dependence on physical quantities, we were able to derive certain laws. We were able to derive ideal gas equation. We were able to show that the pressure of a gas is 2/3 of the energy density of the gas, and we were also able to derive the equation for adiabatic process in an ideal gas. Now we will try to discuss and study these systems more closely so that the other properties of the system can also be found out. Let us recapitulate the idea of phase space, which we have discussed in semester 5 while we were studying classical mechanics, because there is great use of that concept of phase space in statistical mechanics. In classical mechanics, the state of an atom at any instant of time is specified by its position r and momentum p. The 6 components of these quantities, 3 components for r, x, y, z, and 3 components of p, which are px, py, pz. So the 6 components of these quantities span the phase space of one atom. So for n atoms, the total number of degrees of freedom will be 6n. For one particle, for one atom, there are 6 degrees of freedom, 3 coordinates and 3 momenta. So for a system of n atoms, the total number of degrees of freedom will be 6n. Remember, that means we are considering to be free from any constraints. So the motion of these atoms of the system is not having any constraint over it. So we are considering a 6n dimensional phase space. 6n dimensional phase space. In this phase space, the motions of individual particles are governed by the Hamiltonian given by h, the Hamiltonian as a function of p, the momenta, and r, which will be summation over I from 1 to n. Capital N is the total number of particles, pi square by 2m plus 1 by 2 summation over I, which is not equal to j, u function of Ri minus Rj. One should understand that Pi for ith particle will have 3 components. So Pi x component, Pi y component, and Pi z component. So that Pi square will be Pix square plus Piy square plus Piz square. U, which is a function of R, is the interatomic potential, and the factor half there appears to avoid duplicity of the terms. I equal to j doesn't mean anything because that would mean the potential of a particle due to the particle itself. So that will not be there. So potential U is of a particle due to the presence of the other particle. When we take a system of non-interacting particles, this term U will vanish from this equation. we know that the Hamilton's equations of motions, Hamilton's equations of motion are written as Pi dot equal to minus dou H by dou Ri, and Ri dot equal to dou H by dou Pi. Now, in the absence of external time-dependent forces, Hamiltonian H has no explicit dependence on the time. The value of the Hamiltonian is the energy which is constant of the motion, because that we have already seen in classical mechanics. If the external force is not present, which has a dependence on time, then the energy will be a constant of motion, and Hamiltonian represents the total energy over here. The shorthand PR, when we write it like this, the shorthand PR denotes all the coordinates and momenta. The set of coordinates and momenta is denoted by this under bracket PR. Now this 6n dimensional space spanned by PR is called toy space. That 6n dimensional space is called toy space. Now a single point in this space, in this toy space, represents the state of an n-particle system. A single point in toy space represents the state of an n-particle system at any given instant of time. This is so because a single point in this 6n dimensional space will give 6n values, 3n coordinates and 3n momenta. And these 3n coordinates and 3n momenta will correspond to the system having capital N particles. As time evolves, this representative point traces out a zigzag trajectory which will never intersect itself. We understand that the trajectory will never intersect itself, as the solution to the equation of motion with a given initial condition will be unique. As the total energy of the system is conserved, the representative point corresponding to the system will always lie on an energy surface which is called hypersurface in toy space. Hypersurface in toy space defined by H function of PR is equal to E, that is the constant energy surface. This constant energy surface, which we call hypersurface, is schematically shown as we are showing it in a diagram. As we have shown in the diagram, there is the energy surface in the toy space, which we call the hypersurface, and on that surface the zigzag path is the locus of representative point. So representative point, which represents the state of a system at any moment of time, moves on this constant energy surface in a zigzag manner. Alternatively, the representation can be taken in a 6-dimensional mu space. 6-dimensional mu space, which is also sometimes called momentum space. So this representation can be taken in a 6-dimensional mu space where each point will correspond to the state of a single particle. Hence, in all there will be total capital N points in that mu space, which will represent the whole system. In mu space, all these points continuously collide against one another and the aggregate swirls like a cloud. The aggregate moves like a cloud. It swirls like a cloud. So this is how the representation of the individual particles, which will form the system as a whole, will look like in mu space. So each particle is represented by these dots. So when the system progresses with time, when the system is moving with time, this whole group of dots will move together, just like the piece of cloud. So that's why we say that the aggregate will swirl like a cloud. These particles will collide against one another continuously, because as they move, their position and momenta will change. An ideal gas, which is a low density limit of a real gas, satisfies all the above mentioned conditions to be satisfied by a system that we are going to consider. However, one should remember that an ideal gas is not one with no interaction, but this is one for which interaction potential in the limit approaches zero. Let's talk about distribution function. Distribution function for a system of particles. Remember that we are interested in the statistical properties of the atomic system or system of particles rather than the behavior of the individual atoms. So we are not concerned with how does individual atom behave. We are concerned with how does this whole group behave. In particular, we wish to calculate the distribution function rho, which is function of, in general, R, P and T, defined as follows. We divide mu space into cells, which are 6-dimensional volume elements. These are 6-dimensional, given by delta tau, and that is equal to delta px, delta py, delta pz, delta x, delta y, delta z. So the volume element delta tau in this mu space is a 6-dimensional space, and that is the product of delta px, delta py, delta pz, delta x, delta y, delta z. What is this cell? A cell is assumed to be large enough to contain a large number of atoms or particles, and yet small enough to be considered infinitesimal on a macroscopic scale. So as compared to the volumes that we considered on a macroscopic scale, these volume elements or these cells will have infinitesimally small volume, but the cell size should be large enough to contain a large number of particles in it. So, from a macroscopic point of view, atoms in the ith cell have unresolved positions. Unresolved positions means for all the particles within that particular cell, we'll assume to have same coordinates, in same space coordinates, same values of x, y, and z. So the particles present in a cell have unresolved positions, and we represent those positions by Ri, and they have unresolved momenta pi. That means for all the particles we will consider same momentum or same set of momenta, let's say pi. So for the ith cell, all the particles present will have the coordinates Ri and momenta pi, and that means they will also have a common energy, unresolved energy, epsilon I given by pi square by 2m. The number of cells in cell I at any time t is called occupation number. Occupation number. So occupation number for a cell at any moment of time t is represented by Ni, and that is the number of particles present within that ith cell at that moment of time. The distribution function is the occupation number per unit volume. So distribution function, which we are trying to define. So distribution function is the occupation number per unit volume of the cell. So rho, which is function of Ri, Pi, and time, when we multiply this with delta tau, that's the cell volume, that gives Ni, the number of particles present in the ith cell at that moment of time t. So in general, the distribution function rho is a function of time. Further, summation over I, Ni will be total number of particles n, because when we add up all the particles present in all the cells involved, that will be the total number of particles, and the total energy E will also be given by epsilon I and I summed over I, that is the total energy E. The unit for the phase space volume delta tau is, so far we have kept arbitrary. This does not lead to any ambiguity when rho and delta tau appear together, because that will give the number. But when rho appears alone, as in the case for the expression of entropy that we will see later, we will have to attribute undetermined constants so that it may have a meaningful value in terms of entropy. In the thermodynamic limit, where we have taken n tending to infinity, v tending to infinity, so that n by v remains constant at any predefined value. So in thermodynamic limit, we will assume that rho rpt delta tau approaches a continuous function, and we will regard delta tau then as mathematically infinitesimal. Means delta tau will be represented as d3p, d3r. d3p means dpx, dpy, dpz, and d3r means dx, dy, dz. So in thermodynamic limit, rho delta tau rather, will approach a continuous function. And in that case, when we write for this summation, it will change to rho rpt d3p d3r equal to total number of particles. When we integrate it for total range, that is from minus infinity to plus infinity for r, and minus infinity to plus infinity for p. And the total energy E will be represented as summation integration from minus infinity to plus infinity rho rpt into p square by 2m and d3p d3r. So that will be the total energy E. So in thermodynamic limit, these two summations will be replaced by these integrations. This is for the total number of particles n, and this is for the total energy of the system E. Further, if the density of distribution is uniform, this means it will be independent of R. So we will write for distribution function, instead of function of R, P and T, it will be function of P and T. So this equation now will change. We'll write this as rho Pt d3p. Now d3r is dx, dy, dz, and when we integrate minus infinity to plus infinity, and that also from minus infinity to plus infinity, it will be n. The integration of rho over p and the integration of dx, dy, dz means x, y, z are now independent, because rho is no more a function of position coordinates. But what will it result in? If I write, this will be minus infinity to plus infinity rho function of p and t d3p, and this integration will give us v equal to n. Now why so? Why will this v come in? That can be understood if we take the space where this distribution of particles is there. Suppose that is the space where the distribution of particles is present within this volume, which is V. Then the value of rho outside this volume is 0, because there are no particles outside this volume. So whatever non-zero value of rho is, that is within this volume V. So when we integrate for x, y, z from minus infinity to plus infinity, only that volume will be relevant within which the particles are distributed, because outside that volume rho will be 0. Hence, when we integrate dx, dy, dz from minus infinity to plus infinity, the effective value of this integration will be the volume where the particles are distributed. So we can write now this equation as integral minus infinity to plus infinity rho pt d3p equal to n by v. Similarly, this equation will also change and we will get rho function of p and t p square by 2m d3p integral minus infinity to plus infinity equal to E by V. So that is the situation when the distribution function becomes uniform. Now the distribution function evolves in time according to the microscopic equations of motion, which are the Hamilton's equations of motion, and we assume that it will eventually approach a time independent form given by rho function of r and p, which corresponds to thermal equilibrium, because with time this distribution function is not changing. Now we will try to find the equation, we will try to find the equilibrium distribution or distribution function when the system has reached equilibrium, and we will also try to deduce the thermodynamics of the ideal gas from this. The ergodic hypothesis says that the representative point in toy space corresponds to a state of the n-particle system, and this point traces out a trajectory on an energy surface as time goes on. After some time, long compared to the collision time, which is about 10 to the power minus 10 seconds for a gas at STP, the trajectory should reach some kind of steady state which corresponds to thermal equilibrium. Now we know from mechanics that for n, that is total number of particles, greater than 3, the motion is generally chaotic in the sense that 2 points initially close to each other will diverge exponentially with time. So at successive time intervals, which are large compared to the collision time, we expect that the trajectory in toy space performs a random walk over the whole energy surface, as we have talked earlier. This is the essence of the ergodic hypothesis. More precisely, one can prove the following for certain artificial systems, that given a sufficiently long time, the representative point of an isolated system will come arbitrarily close to any given point on the energy surface. So if you take this energy surface in a toy space, every point on this energy surface on which the system is moving or system point is moving represents, each individual point represents a particular microstate. So if you take any point, say this point on the energy surface, that represents a particular microstate. And as we have mentioned earlier, from equal a priori probability, each microstate is equally probable for or equally available for a system, which means the probability of the system being found in any of the allowed microstates is same, means when the system point or representative point is making a random walk on the energy surface. When we give it sufficiently long time to observe, that system will come very close to this point, or you choose any point. If we take this point and we give sufficiently long time, then we will find that at some point of time the trajectory of the representative point is such that it comes very close to this point also. So that means effectively all the points on the energy surface are equally probable when to be close to the representative point when we observe the system for sufficiently long period of time.